Today's video is going to be super interesting. We're going to be finding all of the neighborhood pixels of any pixel we specify in an image. So that's going to be really cool and really useful. So if you've been following along with the series where we're doing image segmentation via graph cuts, then you might remember we're at a point now where we essentially want to determine the edges of all our nodes, which represent our pixels. Now we can do that in multiple ways. The reason I'm doing this video is, and we might not do this as a final version, but the reason I'm doing this video is just to give you an idea of exactly what it is that we're trying to do. It's going to be super clear, super concise. I'm going to go through everything line by line, and what we're going to end up with is hopefully some, useful information. Right, so we should begin by just creating a empty file. I've called mine getNeighbours.py. So once you've done that, you want to open that. So it's getNeighbours.py. And this is just an empty file, and the first thing we're going to do is import a couple of things. We're going to import numpy as MP, which is what we're going to be mainly using, and we also want, what I'm like, I always like to visualize things and plot things just to make it easier for you guys, and for myself also. So matplotlib .pyplot as plt. So what we want to do next, so remember the whole idea of this series, even if you're watching this as a standalone video, what we want to do is we want to convert an image into a graph, and the information we essentially need is how does any one pixel relate to all the pixels around it. Now it doesn't matter if it's going to be very dependent on how many pixels we want it to affect, but in this video we're just going to be doing it based on a Euclidean distance. In another video we'll probably complicate it a bit more as well. So we're going to start now by, I'm just going to basically create an image rather than working with a real image, just so it's much smaller. And we're going to do mp.random random, and we want any value to, it's basically going to be a grayscale image, just to simplify it even further. So what are we doing here? We're creating a random image, I suppose, which is just going to consist of values from 0 to 255, and it's going to be 4 rows and 4 columns. So it's 16 pixels in total, and we're just going to do plot.imshow, and we want to do a couple of things here. Firstly, what do we want to display? We want to display our image, and we need to make sure that our CMap is grayscale, because otherwise we don't have enough pixel values, if you will. We would need RGB values. And then we can just do plot.show, and we're going to, that's the very first thing we're going to do now. And let's go back to our command line and execute our Python script. And this is the image we've essentially created, right? So we've got 4 pixels, 4 rows and 4 columns, and they hold different values. So this is going to be different every time, of course, because we're randomizing it, but it doesn't really matter too much. I just wanted you to get an idea of what we're working with. So we're in a great place now. We've created our super simple 4x4 image, which is a grayscale image, and it's just to give you an idea of what we're going to be working with, just to give you a visualization. What I want to do now is define 3 variables, and that's going to be the width and the height, and that's just going to be equal to our image dot its shape. Now, of course, these are just going to be equal to these values, so we're going to have the width is 4 and the height is 4, and if we change that to 5, then our height would be 5, and so on. I also want to define a variable that we're going to call the index, and it's probably better for me to just show you what the index will be. So we chose 5, and we're going to say the index is 0, 1, 2, 3, 4, 5. So it's essentially, our starting at 0, it's the pixel we have at position 5, and what we want to work out in this video is how does the surrounding pixels relate to this pixel. So we'll be looking for this pixel, this pixel, this pixel, and this pixel, and depending on which Euclidean distance we choose, maybe also these pixels. So that one, this one, and the top left one. But that's getting ahead of ourselves, so let's just ignore that for a moment. Remember guys, we're trying to pinpoint all the surrounding pixels of our chosen pixel at our particular index. So for that, it will help if we knew what row and column we're on, so we can kind of look above, below, to the left and to the right. Now as it is, we can actually determine that, or we can extract that information just based on the width of our image, and the index with two little neat operations. So if we just get started, we're going to define our row and column as the following. We're going to use floor division and the width of our image to get the row, and we're going to use what we're going to use. We're going to use our index, and we're just going to use the modulus operation with the width to get our column. Now I've tried explaining it a couple of times, but really the best way to do it is to just play around with it, and then you'll see why it works. And, I mean, you can kind of see, you know, if you have an index of 5 and you have the width of 4, then you're going to get a remainder of 1, which takes us onto the next row, and it's to do with the fact that it's always going to be, you know, a multiple of the width, so we can kind of determine where we are in this grid. Anyway, let's continue. So if we go ahead and do a nice print statement now, and we're going to say the row is at this placeholder, well, and then our column is going to be at the following placeholder. Now this is just a simple format statement. You probably have seen this before, but it looks neat in my opinion, so I'm doing it. And let's go ahead and execute this Python script. And that's our image. Doesn't really matter too much, and we do in fact get the information that our pixel that we chose, which remember was here, is at location on row 1, column 1, which is exactly correct. So the next thing we want to do now is to create our pixel neighborhood, if you will. So that's going to consist of the pixel that we have at our index and all of the surrounding pixels within a certain radius, which we're going to predefine for now as 1.2, but again that's going to be slightly later in the video. So the first thing I'm going to do is define this variable r, which is just going to be an integer version of our radius. Now this is turning our 1.2 into an integer, which is just going to equal 1. And the reason we're doing this is just for a particular calculation, so just stick with me and all should be good. Now next we're going to create two lists, and these lists are both going to hold the vertical and horizontal neighborhoods. So again, our neighborhood, if we just go ahead quickly and execute our Python script, let's tidy that up by doing a new one. That doesn't help. Let's go back. Okay, so our neighborhood is everything around this black pixel in this particular case. So we want to create a list of these values and a list of these values. And we possibly, like I said, care about these values. We're going to include those in just a moment. So, okay, so we've got that. So how are we going to do this? Well, we can use x equals mp.arange, or arange. And what this does is, so for example 0, 3, I'm just going to show you what's going on so you can kind of stick with me. Maybe you already know numpy. Let's close this. So we've just created a range 0, 1, 2. So things to note here is that it starts at 0, but it doesn't include 3. So it starts at 0 and it's of a size 3 elements. Okay, so that's what we need to note here. And instead of having 0 here, what we're going to have instead is we're going to get the maximum value of this expression. Now this is either going to be our column minus our radius, and again we'll look at that in a moment, or it's going to be 0. Now in the particular case that we just did, our column is 1 and our radius is also 1, so this is going to be 0. So we are in fact going to be starting our range at 0, which makes sense, remember, because on column 0 is both on column and row 0 we've got neighboring pixels, which is what we're looking for. So min then is going to be similar, but it's going to be in the opposite direction. We want to find the minimum value here, and that's going to be either the width, which makes sense, and this is going to be plus r. Let's make it look the same, plus 1. And why are we doing the plus 1? Because we noticed just a moment ago that when we specified our a range to 3, it didn't actually include the 3, right? It just went to 2. So it was a size 3, but it went 0, 1, 2. So we're adding plus 1 to make sure it's the correct length. So everything here seems to be in order. Okay. So next we want to do the same with height. and we want to do it with width. And when I say width, of course I mean row. So what we're, and this needs to be y. So essentially now we're creating here a bunch of y values. We've got our y values and x values, which are both going to be 0. If you do the logic, they're both going to be 0, 1, and 2. And you might be like, well, what's the point in that? They're not our values, but it's so we can. You'll see. This is going to allow us to create a mesh network, which then in turn is going to allow us to do some Euclidean mathematics like Pythagoras theorem. So that's basically where we're going with this. So next I'm going to create a mesh grid for you, which I'm then going to display for you so you can see exactly what is going on, and it will help me to. So we're going to plot this. Now a mesh network is, I'm not even going to explain it, but essentially, yeah, no, let's just keep it like that. I'd rather show you rather than trying to explain it with words, because it's just one of those things. Our marker is going to be dot. That's going to represent our grid, and we want to make that black and line style none. I don't know if we need this, probably not. And we're going to do plt.show, and I'm actually going to comment these out. We no longer care about that really. Column is not defined, so we've got y is column not defined. We got rid of our previous things, so I must have deleted that by mistake. Luckily I've got it saved here. That should work. Column is still not defined. Let's change this to column. And I put lifestyle. Did I? No. No, object has no property line style. It says liney style. Right, let's tidy this up. Voila. This is what we wanted, and that's what we've done with the few previous lines of code. So this is our neighborhood now, right? Well, somewhat. This represents our pixel that we called our index pixel, and then we've got pixels to the left, right, top, bottom, and in the corners also. So this is what we were trying to do, and now what we want to do is say, hey, what pixels are within a range of 1.2, like our radius 1.2. Now we know the distance from here to here is 1.1, is 1, and down here also, and all these pixels are 1 pixel apart, right? So all of them have a radius of 1 relative to each other, but these diagonal ones don't. So the distance from here to here is going to be 1 squared plus 1 squared, and it's going to be the square root of that, which will be the square root of 2, which will be approximately 1.4, which again is less than 1.2, is more than 1.2, sorry, and is not going to be part of our neighborhood. But if we change this to 1.5, it would be. So this is that's where we're going with this. So continue. So now we're going to comment these out momentarily. Create R. R is going to be, like I said, it's going to be Pythagoras' theorem, and we can use the square root function. And inside our square root function, we are going to have a couple of things. There's going to be an addition, of course, and then we're going to have these two. So we're going to be adding that, and then this is going to be squared. What's that going to be? It's going to be x minus col squared. And you can check that yourself if you want. And then we're going to have y minus rho to the power of 2 also. So what we're saying here, it's going to be the square root of x minus the column and y minus the row, which then is going to give us the distance of each one. So it's going to return a matrix of values. So it's going to be really neat. Let's tidy that up a little bit. Bring that in. Make sure everything is closed. I almost feel like no, this looks good. So let's print R. I've done it again. Column. Okay, there you go. So we should probably display this actually, but you probably know what's going on now. And then one more time, just so we have all the information. Okay, so we've got our grid, and what we're basically saying is that this is our index pixel, so the distance to our index pixel is 0, that's to be expected. To this one it's 1, 1, 1, 1, and then 1.4, 1.4, 1.4, 1.4. We only care about the distance, we don't care about direction or anything, so they're not negative, they're all positive values. That's okay. So what next? Next we want to create a new matrix, which we're going to call mask, and we're going to basically say it's going to hold the values of R, but it's not going to hold the values, it's going to hold true or false. And we're basically going to say, look, if R is less than 1.2, then that particular element is going to hold the value true, otherwise it's going to be false. It's probably easier to just show. Sometimes words just go over your head. So there you go. We already knew that 1.4 is bigger than 1.2, so we've got this. This is our neighborhood. All these ones are, as far as we're concerned, in terms of Euclidean distance at least, which is only one metric you can use. We could also use the actual color value, which we'll do later. As far as Euclidean distance is concerned, these are the only pixels that are actually in the neighborhood of our index pixel 5. So we've created that. So this is great. We've got our mask now, which is going to be super useful for us. And remember, our mask is telling us which pixels are actually part of the neighborhood and which aren't, based on our radius. So what we want to do now is apply that mask to our x values and y values here, and I'll talk through just y in just a moment. So we want x mask. We're going to print this, and I should probably have a print statement as well so we know where we're at. So x mask, and let's just copy all of that down below. So we want y mask as well, please, and we want y here also. So firstly, what are these two? Well, x and y, if you remember, they allowed us to create the mesh grid, which is the graph that we see. Let's plot it. Not this one, this one. So basically they hold the values, the column values and the row values for all of the potential pixels in our neighborhood, right? But we don't care about all of the pixels in our potential neighborhood. We only care about the ones that are now not being masked. So we care about this little cross in the middle. Those are the values we want. So all we have to do now is apply our mask to it, which we've done, and then what we end up with is in that particular neighborhood the locations of all of the pixels we care about. And actually, let's execute this again so I can just show you. So remember, y represents the row values and x represents the column values. So if we go through this quickly, what we're saying is, remember, our index was 5, so this is the pixel at the center of our neighborhood, and what this is now showing us is, okay, well, one of the pixels in our neighborhood is row 0, column 1, which is this one. Then we move along, then the next one is column 0, which is this one, row 1, which is this one. Then we've got one at column 1, row 1, and column 2, row 1. And then finally we go on to row 2, which is all the way down here, and we go to column 1, which is here. So this is telling us that this is our neighborhood. So hopefully you understand that. So if we quickly were to change this, for example, to 1.5, and make sure, by the way, you change this to radius, because I hadn't done that. This was a float number we had. So come down to mask equals r, it's less than radius. And based on what I just said, we should have 4 more values now, remember, because it was 1.4 was the cutoff, and we've put it up to 1.5. So you can see that we've got way more values than we did before, and there will be 4 more values because they're all true. So that's what we're doing. So now what? Well, we don't really care about where the positions are relative to the... We don't have all the information yet, right? We want to be able to literally say this pixel in this entire image is part of this neighborhood, so we need to be able to access the pixels by index. That's what we're saying. So we're almost done now. We've literally only got to write a couple more lines of code. Actually, I could do it, yeah, a couple lines of code. So we're going to print this, and then I'm going to talk you through it. That's how I like to do it. Let's focus on the practical parts, then the theory. I don't like to waste too much time on theory. I just think it makes the video too long, and we want to do times the width. explain it. Yeah, and then I'll just do this. So what we've done here is this is going to give us the index of our pixel, of our pixels. And I'll explain to you why it works. In fact, the way I'm going to do this, let's actually make this a bit nicer. I'm going to reverse this. Not that it matters, but I think it's better. And let's just make it, although it's using bitmass, of course, or whatever you've been taught, let's put that in brackets just so it's very clear. We're doing the multiplication and then adding our X mask. And let's talk you through it. So firstly, let's run the script so you can see what the values are, and let's execute again. So you can see that this is our grid now, our image, and this is giving us the exact locations in terms of an index of our pixels if we were to flatten it into a line. So what have we got here? Well, it's given us, the pixel index. So let me just do this quickly. That's right. So at index 1, we've got one of our pixel neighborhoods, and at index 4, and at index 5, index 6, and index 9. So that's exactly what we wanted to do. So we've managed to return the index values of all the pixels that are part of the neighborhood for that particular index. So for 5. So that's what we've returned just on putting in the value 5. So that's great. So how does it work? Why does it work? It's quite simple. If you remember the formula, so we had our y index, which is our rows, and we multiplied it by the width. Why does that work? Okay, so suppose we're on row 1, which we are, and this is row 0. Then we know that the width is 4, okay? So if we're on row 1, then we know that there's been at least 4 pixels, right? So we multiply it by 4 and say, look, we're on row 1, which is our y value, so 4 times 1 is 4, we've got at least 4 pixels, and then all we're going to do is we're going to add the column which we're in, right? So our x value is 1, so we add 1, and then that's going to return the value. Hopefully you understood that. To me that's quite clear. If it isn't clear to you, play with it, ask a question. And again, I always suggest asking questions. I don't even mind that much if you like the video or subscribe, but if you've got a question, you should always aim to, understand. Really understand what you're doing. Don't just kind of get it to work. But anyway, I'm ranting a bit. So there's one final thing we really want to do, but this is a really cool start. But we also want to essentially return the distances, right? Because we'd be using those in the series later. And we can simply do that by using our mask again, which is why it's so cool. So we created that mask, but this time our distances, if you remember, were in this. That was all our Euclidean distances. And we just apply our mask to it, and it's just going to affect this graph. So that's R, and we're going to apply the false. We're going to apply this matrix to it, and it's going to return these in order like it has with these. So we should get 1, 1, 0, 1, 1. That's what should happen, assuming we've made no mistakes. So that's exactly what we got. This is pretty neat. And you can play around now. So if you notice that these values here are 1.414, square root of 2, if we now increased the radius to 1.5, then we would actually just get everything in that original graph we drew. Mesh network, meshgrid, whatever you want to call it. So now we've got these in order, and then these are the pixel indexes of, let's do that again. So just to clarify, so now we're saying that all of these pixels here are in the neighborhood of this pixel, and we can kind of prove that. We've got one at 0, 1 and 2, not 3, but we've got one at 4, 5 and 6, not 7, but we've got ones at 8, 9 and 10. So that's really cool. Now what I would advise, and maybe I'll do that, is to really clean the script up. What you probably want is a class, well, probably just a function or class, whatever you want, which takes some parameters. The only parameters we need, if you've noticed, is we need the index of the pixel we care about, we want the radius, and we need the width and the height of the image, because that's how we calculate, do a lot of our calculations, working out where everything is, and etc. Other than that, we don't need any information. The rest is just worked out mathematically. So that's everything. Hopefully that was useful, and we'll be going further into this series still to actually do the image segmentation. And it might be slightly different to this. I just wanted you to really understand what we're doing. So this is just going based on the radius. Now, of course, when we do image segmentation and we're adding edges to our graphs, we might not just be going on a Euclidean distance, we might also be going on how similar the pixels are, so it'd be a product of the distance and the brightness, or the color, something like that. Probably brightness, because it's a grayscale is a single list rather than RGB, which is 3 values. So we're going to be playing around a bit more, so subscribe, and I will see you in the next video.